In this section, we're going to move away from the idea of estimating the values underneath of curves for areas. And we're going to move towards being able to find the precise values underneath the curve. And we're basically going to take a look at an operation in mathematics called an integral or an antiderivative. The techniques are the same, even though they don't necessarily represent the same thing. So what we're going to do in this series of videos is we're going to make sure that we understand how to evaluate simplistic indefinite intervals, and we're going to define what an indefinite interval is. We're going to develop the fundamental theorem of calculus. We are going to use the rules for the antiderivatives to evaluate definite integrals. And then we're going to take a look at some rules of symmetry to help us in the evaluation of some definite integrals. So in Calculus 1, we spent a lot of time going over the derivative and lots of rules and techniques of differentiation. And then we took a look at applications of that to be able to look at optimization, that sort of stuff. So in Calculus 2, we're going to move away from that. We're going to really primarily focus on the antiderivative. Okay, it's the inverse operation of the derivative. And so there's a lot of rules for antiderivatives. These are what you're probably going to have to memorize. All right, so going through these, the antiderivative of any constant is the constant times x, as long as we're in a continuous function that's represented by the variable x, which we're integrating with respect to. If you have a constant times a function, it's going to be the constant times the antiderivative. The antiderivative of sine is negative cosine. The antiderivative of secant squared is tangent. The antiderivative of cosecant squared is negative cotangent. Antiderivative of e to the x is e to the x, the easiest one. Antiderivative of 1 over 1 minus x squared is arcsine. And then over here, we can see that there's another list of rules that we should memorize. Okay, so instead of multiplying by n and subtracting 1 for the derivative, we're going to add 1 and divide by that new exponent. If you have the sum of two functions and you want to find the antiderivatives, then you just find the antiderivative of each of the terms that comprises the integral. Here's some trigonometric antiderivatives. All right. And then finally, the antiderivative of 1 over x is the natural log of the absolute value of x, and the antiderivative of 1 over 1 plus x squared is the arctangent. All right. So again, a suggestion might be to make a note card of these because you're going to be using these quite frequently throughout the entire semester. And eventually you're going to memorize them. But for right now, since we might not have them memorized, it might be beneficial for you just to have that list on hand on a note card so you can reference it quickly. Now, indefinite integrals. An indefinite integral is basically going to be finding an antiderivative and then just tacking on a plus c at the end, all right? And the plus c is a constant of integration. And one of the ways that you can check to make sure that you got your antiderivative or your integral right is just finding the derivative, all right? So if you find the derivative of this, you should get back to your antiderivative or your original function, all right? So this way is an antiderivative, okay? And you kind of just keep that in a cycle. And remember, when you take the derivative of a constant, it's 0. So that's why it's an arbitrary constant, is because it can just represent anything, all right? And when you take its derivative, it just goes away, whether it's 5 or square root of 75 or pi, whatever it might be. All right, now, in this particular video, all we're going to do is take a look at 4 problems to where we go through and find the specific antiderivatives or the indefinite, evaluate some indefinite integrals. All right, so our first one we have this 2x squared plus 3x, I'm sorry, 2x plus 3x squared plus pi with respect to x. All right, now, we're not going to do this every time, but technically what we're doing is we're taking the antiderivative of the sums. Okay, so that's going to be 2x dx integral 3x squared dx, and then integral of pi dx. Okay, so technically that's what we're doing. We're probably going to get to the point where we don't go through and split up into 3 integrals. Now, what we're going to do is we're going to add 1 to the exponent and then divide by that new exponent. So this is going to be 2x to the 1 plus 1, which is 2. And then we're going to divide by 2. All right, so that's the antiderivative. Finding the antiderivative of 3x squared, we're going to add 1 to the exponent So 2 plus 1 is 3. And then we're going to divide by that new exponent. Anytime we have a constant, and pi is a constant, we're going to add an x to it. So that's going to be pi x. And then antiderivatives or integrals are going to, for indefinite types, are going to have a plus c. If we simplify this, we get x squared plus x cubed plus pi x plus c. And that's our answer. Okay. If we wanted to check this, we would just take the derivative of this. Okay. In fact, this is a really easy one. So just illustrating that we could take the derivative and get back to the original integrand. We know that the derivative of x squared is going to be 2x. We know that the derivative of x cubed is going to be 3x squared. We know that the derivative of pi x is pi. And we know that the derivative of any constant is 0. And notice that this is precisely what the integrand is. Okay, so that's how you can check your answers. Okay, eventually you'll get to the point where you just feel confident enough that you don't have to do that. But for right now, it might not be a bad idea for you to take the derivative of your solution just to check to make sure that it does make sense. Okay, another example. We have this 3 sine x minus 2 sec tan x, sec x tan x, and 7 e to the x minus 9 over x. Now, what I'm going to do is I'm going to split this up. I'm going to factor the 3 out, and we have sine x dx minus 2 integrals of sec x tan x dx plus 7 integrals of e to the x, and then finally minus 9 integrals of 1 over x dx. So notice what I did. I just factored out the 3, the -2, the 7, and the -9. And then I just split it up into 4 separate integrals by using that sum and difference rule. Right? Now, I can perform the antiderivative. And again, it's helpful to have this list. We know that the antiderivative of sine is negative cos. Antiderivative of e to the x is e to the x. Antiderivative of 1 over x, natural log of the absolute value of x. Antiderivative of secant tangent x is secant x. Okay, so when we go back down, we just rewrite these, and this is going to end up being -3 cosines of x minus 2 secant of x. Okay, so that's this and this one. We have 7 e to the x minus 9 ln absolute value of x, and then because it's an indefinite integral, we have a plus c for our constant of integration. Another example where we have some radical expressions, we're going to treat these just like they were going to be a derivative. We're going to prepare it for differentiation, or we're going to prepare it for integration. So we know that instead of, we could just rewrite this as x to the 1/3. So we have a third root that's the same thing as the 1/3 power by using our rational exponents. We're going to make this -6x to the 7 into negative, or 6 over x to the 7 as -6x to the -7. So we have the negative exponent rule. And then finally, -2x to the -1/2 dx. Okay, so just like derivatives, what you're going to do is you're going to prepare it for integration by using the same algebraic techniques. Now you can split it up if you want into 3 separate integrals. So there's the integral of x to the 1/3 dx minus 6 integrals of x to the -7 dx minus 2 integrals of x to the -1/2 dx. Okay. Now we can go ahead and find the antiderivative. We're going to add 1. So it's going to be x to the 4/3, and we're going to divide by 4/3. We're going to add 1. So we have the 6. Adding 1 to -7 is -6, and we divide by the -6. And then we have -2. We're going to add 1. So that's going to be 1/2 over 1/2. And then we have the constant of integration. Finally, we're going to clean this up. And to clean this up, we're going to take the reciprocal. So this is going to become 3/4. And then if we wanted to move it back as a radical expression, that would become 3rd root of x to the 4th power. -6's are going to cancel out. We have x to the -6, which we could write as 1 over x to the 6th. 2 divided by a half is going to turn into 2 times 2. We have a negative, that's 4. We can make the 1/2 x or the x to the 1/2 into a square root of x, and then we have a plus c. All right, so that's our antiderivative. If you don't trust it, you can certainly take the derivative of that antiderivative and get back to the original problem. Right. Now, this one looks like it's tough, but in fact, this might be the easiest of all of them that we've done. So we have the quantity of x plus 2 times x minus 4. We're going to start by FOILing this out. Okay, so if we multiply it out, we're going to get x squared plus 2x minus 4x minus 8. And then we can just combine the inner terms there to get a negative 2x. So I'll just erase that. Okay, and now we can just integrate term by term. Antiderivative of x squared is going to be x cubed over 3. We're going to add 1, divide by 2. Antiderivative of a constant, we just stick an x at the end of it. And then finally, we have our constant of integration c. If we were to simplify this just a little bit, we could rewrite this as 1/3 x cubed minus x squared minus 8x plus c. Again, it may be beneficial for you to take the derivative of this solution to make sure that you can get back to the original integrand. All right, so that's how we go through and we evaluate indefinite integrals. Okay, so indefinite integrals, no limits of integration, but we have a plus c at the end. It's an arbitrary constant of integration. Now, in the next video, we're going to learn how to evaluate definite integrals. And this is the technique that we're going to utilize throughout the remainder of the semester, except for a couple other portions, to get the precise areas that are bound by a curve in the x-axis.